So what happens when a solution forms? Think of a solution as a mixture of A and B, and as we've discussed previously, a solution must be uniform in its composition and in its concentration throughout. And what will happen is, suppose A is the solute and B is the solvent, so say A is salt and B is water. What you see happening when you first mix them, the salt is going to be by itself, the water is going to be by itself. And what we want to happen is for the two to mix, so that the salt is surrounded by both salt and water, and the water is surrounded by both salt and water. And that will form a uniform solution for us. And in order for this to happen, what we need to do, energetically speaking, is disrupt the energetics of A to A, which takes energy, disrupt the energy of B to B, which also takes energy, and then form A-B interactions. And this gives us energy. So this releases energy. This is exothermic. So this is something that's good for us and is favorable thermodynamically. So what we want to do is kind of see how this plays out. We're not going to calculate it much in this chapter, but I want you to understand the dynamics. Okay, so when salt and water mix, we need to break the salt to salt interactions, we need to break the water to water interactions, and we need to form salt to water interactions. This takes energy, this releases energy, provides energy. Okay? If A and B interactions are large enough to overcome this, then the solution will likely form. Okay? And we have a heuristic that says like dissolves like, meaning that if A and B are alike, polarity-wise, like if they're both polar, they will likely form a solution. If they are not polar, both non-polar, they will likely form a solution. If we mix polar and non-polar together, they likely will not dissolve one another. That's the heuristic. Heuristic meaning rule of thumb. So the rule of thumb is that like dissolves like, and we'll discuss this in a minute as well. Okay, as far as the energetics goes, the heat of solution is equal to the heat of breaking A, which is positive, the heat of breaking B, which is positive, as I outlined here, plus the energy of mixing, which is negative. Okay, so we add them up together, and that's the delta H of solution. And delta H of solution for a variety of solutes is tabulated for many of them. You can find them in the backs of books, in the back of our book too, and some of them are negative, some of them are positive. And let's discuss what that means. If breaking 1 and 2 requires more energy than forming a 1 and 2 together, then we have an endothermic heat of mixing, because it requires a net amount of energy to do. Conversely, if mixing again, this interaction is larger than these two, we will form an exothermic heat of mixing, heat of solution, and this is more likely to occur for an actual solution. And just as an example, if you mix water with sodium hydroxide, which is Drano, the dissolution process is going to be highly exothermic, and if you touch it, it's going to be very, very hot. The cup that you're mixing together is going to get really, really hot. Whereas if you mix water and potassium bromide, the cup will get cold because it requires energy from its surroundings, and it takes a long time to actually mix because energetically this is not favorable. Okay. Again, like dissolves like, how do we overcome this barrier? We can reduce the value of A and B, or we can increase the value of delta H of mixing. And we want to increase this because it's negative, and if this is negative, it's more likely to occur. How do we do that? If A and B are sort of alike. If they're alike, delta H of mixing will be even more negative because they will release more energy by forming this. And this is where the heuristic comes from. Polar molecules dissolve polar molecules, and nonpolar molecules dissolve nonpolar molecules. And let's look at an example to kind of showcase this. Which of the following pairs will likely form solutions when mixed? So, in order for us to do this, what we need to do is determine which is polar and which is nonpolar. And then two polars will mix, two nonpolars will mix, but a polar and a nonpolar will not mix. So in this scenario here, CCl4 is nonpolar. C6H6, benzene, is also nonpolar. Okay. Methanol here is polar because it's tetrahedral with one OH, but methane here is nonpolar. KBr is ionic, and therefore it is polar, or ionic. Water is definitely polar. Carbon dioxide is nonpolar, it's linear, and methane again is polar. So what we'll do now is just see which one is like dissolved like. So we see that this should occur, and this should occur. And indeed, forming methanol in methane doesn't really occur. Carbon dioxide in methanol also doesn't really occur. Okay. Now let's talk about saturation. When we're mixing a solute and a solvent, okay, there's a limit as to how much the solute can go into the solution. And I think you've seen that, I'm sure you've seen that, when you mix a cup, say, of sugar water. If you add a lot of sugar, eventually the sugar will not be able to dissolve in the water, and what you'll form is a cup that has sugar at the bottom. The water itself is still very sweet because it dissolved a lot of the sugar, but it can no longer hold any additional sugar. So as far as this goes, if you begin with just pure water at first, you can add sugar and keep adding sugar. This solution is known as unsaturated, meaning that there's more room for additional sugar. You keep adding sugar and more sugar and more sugar, and the solution is still unsaturated until it reaches a limit. That limit is called saturation, and that is the maximum amount of sugar that could go into the water. And that solution is known as a saturated solution. Any iota of sugar beyond that limit will cause sugar to come out of the solution. It will not come out of the solution, I'm sorry. It will not allow that additional sugar to dissolve, and we will form a cup, like I said, with some powder at the bottom. The cup itself, the water, is a saturated solution of sugar water, and any additional sugar will just go to the bottom. Okay, and you can see these pictures here to kind of explain unsaturated and saturated. If you have a bed, in this particular bed, the woman has probably room for another person to lie down in a mattress. So we say that this situation is unsaturated. This mattress can saturate more, can take in more people. This is a comfortable scenario, presumably with two people in a bed. That's what it's designed for. Large beds are designed for, presumably. So we say that this bed is saturated with people. Okay, so that's kind of like the analogy of the sugar water in the cup. Okay. Now I want to talk about something that doesn't often happen, but sometimes could occur, and that's supersaturation. Okay, this occurs when you're slowly adding solute to the water, and you can sort of trick the solution, and it will take in more than the limit is set, and that is known as a supersaturated solution. When you have a supersaturated solution, as I said, you're beyond the saturation limit, and you can sort of this trick occurs, but if you disturb the solution in a certain way, like raising the temperature, adding some crystal in there or something like that, it will remind the solution that it is oversaturated, and things will crash out. Okay, that's not a very it does occur in nature, and we do utilize it to purify certain compounds, say when we're trying to extract minerals or extract other valuables from the ground and things like that. But as far as day-to-day life, I don't think that this occurs very often. But nevertheless, I do want you to understand this. And as far as the picture goes, if you look at this bed, this is super saturated. There are way too many people in this bed. They're all asleep, right? As soon as they wake up, they'll realize this is ridiculous and they'll get out. And that's the same idea with the solution. It's super saturated. It is quote-unquote sleeping, and as soon as it wakes up, it realizes it's ridiculous and it comes out of solution, and it will form a crystal at the bottom. Not super common. I want you to concentrate on these two very, very much, and you could see these in a graph this way. This is sort of like a phase diagram of salt and water. Right. So in this particular thing, I'm showing you here the percent of salt that I could put into the water. Suppose I'm at 0 and I only have water and I'm at 25 degrees Celsius. This is just water, and if you drink it, it will just taste like water. You can start adding salt and add more and more and more salt. And this is an unsaturated solution. Okay? And this means if I'm here, I can add more, and I can add more, and I can add more, and I can add more until I reach this black line. At this point, if I stop, this is a saturated solution right here. And this is known as the solubility. So the solubility of salt in water at 25 degrees Celsius is about 30-31% or so at room temperature. Okay. If I go beyond that, okay, now I'm forming two phases. The salt water, which is saturated, right? The cup that's just got salt in it, and some salt, NaCl, at the bottom that doesn't even get mixed. That's what I'm forming. I'm forming two different things that don't mix anymore. And this entire area, until I reach 100% salt, is a mixture of the two because they can no longer mix. Here they can mix up to a point. Beyond that point, they can no longer mix. And this is a saturated solution, indicated by this particular point. It's about 31% salt and water. And then any additional salt just goes to the bottom and does not go into this water. Okay. As you can see also, solubility increases with temperature. So if I'm here and if I'm here at 25 degrees Celsius and I have 30% or so water, salt and water, if I increase the temperature, let's say to 40 degrees, right here, I can actually add more salt, and then this here it will still be unsaturated, and I can add more until I reach this point. So the actual saturation limit increases with temperature, and it also decreases with as you decrease the temperature. Right. This explains the phenomenon known as dew forming on the ground. So you can think of this, instead of salt and water, think of it as water in air. The solvent is air, the solute is water. And air can only take up to a certain point of water in it. Otherwise, beyond that point, it is saturated. Okay. This is known as humidity, relative humidity. When the relative humidity is 100%, you are here. Okay. Up until that point, you'll be beneath it. The air can take more water, and it will reach 100% humidity. And beyond that point, you cannot dissolve more water into the air, and it is no longer going to take it. Okay. What happens is that during the day, let's say it's very humid, it's going to get to a point where it is here, right? And let's say it's kind of 99% relative humidity or something like that, okay? So the air has a lot of water in it. Overnight, the temperature drops rather rapidly. So if it drops rapidly, what will happen is it will go down really rapidly. And now I have a solution, I have a situation where it is beyond the saturation. And all the water that was previously stuck in the air or dissolved in the air comes out as dew on surfaces because it just doesn't get taken up anymore. Okay. Same idea with humidity and solubility. Okay, let's talk about this idea of miscibility. If A and B are miscible in all proportions, like ethanol and water, we say that they're miscible. They can mix and they can they're mutually soluble in all proportions. If A and B can only go to a specific limit, like salt and water or air and water. We say that they're partially miscible and there's a saturation limit. If A and B cannot mix ever, we call them immiscible. And this is a picture here of oil and water. They don't mix, or oil and vinegar would not mix. And these are known as immiscible. No matter what you do to them, they won't mix. Okay. And we'll get back to this at the end of this chapter as how we can trick the solution into doing this. But it's immiscible. All right. So we said that temperature raises the solubility. What about pressure? Well, we've talked about how liquids and solids are incompressible. We cannot compress them, so the pressure shouldn't affect anything with them. But gases do get affected. So if you pressurize a gas, you can force it to dissolve, and that's indeed what happens with carbon dioxide and water. If you want to make carbonated water, carbon dioxide is only slightly soluble in water because it is nonpolar. And the solubility is very, very low. But if you increase the pressure, as you can see in this law here, in Henry's law, if you increase the pressure, you will increase the solubility. This is just a constant. It remains a constant. So for CO2, there's a value here, like let's say 3, I don't know what. The pressure is atmospheric pressure, and solubility is low. If I increase the pressure a lot, like 6 times, I will increase the solubility by 6 times. I can dissolve six times as much carbon dioxide in my water. Okay, this is what bottlers do and soft drink manufacturers do, and that is why a bottle of Pepsi or a bottle of Coke or whatever will be pressurized, because that extra pressure is going to force carbon dioxide into the water. As soon as you open the bottle and you hear the psst, sound, that's carbon dioxide escaping, because you're reducing the pressure back down to atmospheric pressure, and the solubility goes down. And you're reminding the gas, hey gas, you shouldn't be there, and it's slowly leaving, and that's why soda goes flat, because carbon dioxide doesn't really dissolve in water, not that much, and the solubility goes next to nothing. But it does take a few hours to do. If you just leave it open, by the way, it will take much less time. This is Henry's law. The solubility is proportional to the pressure. And let's see it in action in an example here. Henry's law's constant for helium and water is this. Calculate the solubility if helium has a pressure of 1.5 atmosphere. Okay, so as we just saw, the solubility, as we said, solubility of a gas in molar, it's molar, is equal to some sort of constant times P gas. Well, we were given the constant right here. So, and we're asked for the solubility. So it's pretty simple. It's 3.7 times 10 to the minus 4th molar per ATM. Okay. And you multiply this by the pressure of the gas, which is also given to us, 1.5 ATM. I meant for this to be a little simple, so we see it happen. And so you see that the solubility of the gas is just going to be 5.6 times 10 to the minus 4th molar. Okay. So let's take Henry's law and do something else with it. Okay. Let's say that Henry's law's constant 4 and 2 is equal to 6.0 times 10 to the minus 4th molar per ATM. And I want to know that if I have N2 with a pressure of 1.0 ATM, is a solution containing 1 gram of N2 in a liter of water, in a liter of solution, is this saturated or not? So here's what I'm trying to say. I have Henry's law's constant for N2. That's just what it is. It's a constant. And I'm saying that the pressure right now is 1 atm. Cool. Okay. Now I want to say separately, this is just what I know. This is what's given to me. I have this situation where the constant is given to me, and the temperature is 1 atm. Makes sense. It's current conditions. Okay. Now, I have a solution lying around here, and it has 1 gram of nitrogen in a liter of solution. I want to know, is this saturated or not? Is it saturated or not? Okay, how do I find out? Well, let's look. I know that the solubility is equal to K times the pressure of the gas. And I'm given K, again, it's 6.0 times 10 to the minus 4th molar per atm. And I'm given the pressure of the gas, well, that's just 1.0 atm. So that means that I have the solubility, and the solubility here is just 6.0 times 10 to the minus 4th molar. That means that this is the limit at which I can have nitrogen dissolve in water. So I can have 6.0 times 10 to the minus 4th moles of nitrogen per liter of solution. This is what this means. And this is the saturated limit. And again, to go back here and to show you, it's this line here. Meaning anything beyond that, if I'm trying to put anything beyond 6 moles per liter, I'm going to 7 times 10 to the minus 4th moles per liter, or 6.5 or 8 or whatever, it will be beyond the saturation limit. I don't want that. It won't work for me. So this is my limit. So what I'll do is I'm given another solution here, 1 gram of nitrogen in a liter of solution. If I'm going to calculate the molarity of this thing. If the molarity is less than this value, I'm good. I'm unsaturated. Then I'm not saturated. If the molarity is greater than this value, I am beyond the saturation limit. So let me calculate the molarity of that solution. Again, the molarity is equal to moles of N2 divided by liters of solution. Okay, so I gave you this as 1 liter. Okay, I told you that it's 1 liter. And I gave you the mass of nitrogen, not the moles. Well, we can just convert it. So I have 1.0 grams of N2, and I will divide this by the molecular weight, like this. And I will get 0.04 moles of N2. Okay, so now my molarity here is going to be 0.040 moles of N2 divided by 1.0 liter solution, and it is 0.040 molar. Now look at my solubility value. My solubility value, put them side by side. My solubility was 6.0 times 10 to the minus 4th molar, and what I calculated was 0.40 molar. This is far larger than this, meaning that this is beyond the saturation limit. I reached saturation and I went beyond that. 1 gram will not go into a liter of solution.